theory of acquisition, like this one. This is one particular learning theory, right? Many other out there potentially, right? But here's one that we have recently been exploring with my research team. And so the idea is that the child's trying to learn the right building blocks for WH dependencies. And let's dig a little into what that means. And the idea here is that the child's viewing WH dependencies in terms of the building blocks of those dependencies and tracking or counting or otherwise, being aware of the frequency of those building blocks in the input, right? So that's the goal of acquisition, these building blocks and how frequently they occur, and you're trying to figure that out from your input. So in this case, what are the building blocks that we're considering? Dependencies here are going to be represented as a syntactic path, a sequence of structural nodes that contain the gap, but not the WH word. So in what did you see? You have the gap here. It's contained by, in this case, what's labeled a verb phrase and then an inflectional phrase, and then you connect up with your WH word, so you can characterize this WH dependency with this particular syntactic path, the sequence of container nodes. Now, of course, this is like extremely old school syntactic phrase structure. Use whatever labels make you happy. This is fine, but the idea is that there is some path between the WH word and the gap where it's understood, and that's sort of the important bit that's being extracted from the input for the WH dependencies. And you can do this for any WH dependency, like really short one, like what happened, just has a very short path here, versus longer ones, like what did she want to do? Again, it's the path between the WH word and the gap, and you're just sort of following that line of structural nodes, whatever they happen to be labeled. So the idea then is that dependencies that are much less acceptable have low probability segments in them, things that just don't occur that often. And if children break these dependencies, therefore, into smaller building blocks, they can identify if a dependency has bad segments that are made up of one or more low probability building blocks. And so the theory then is the child's trying to learn what the quote-unquote best building blocks actually are. That's what learning is about. And what's best mean? Great question, right? So in here, the idea, the guiding intuition is that the best building blocks are the most efficient ones. So efficient building blocks, what does that mean? The idea is that efficient building blocks will allow the representation of current and future WH dependencies to be more probable. Okay, so why does being more probable make you more efficient? Well, one idea is that higher probability WH dependencies are faster to process, whether you're comprehending them or producing them, and so that's why they're efficient. Okay, so we're learning efficient building blocks, we're learning things that make dependencies high probability. How shall you find these efficient building blocks? And so here the idea is that the child's looking for building blocks that are a balance between how big the blocks are and how fast they are to put together to make a WH dependency. So let's look at that. So suppose we have this dependency. What did she say that he saw? And again, this is a structure that you might be assigned to it, and the child's paying attention to that syntactic path of container structural nodes, right, between the beginning of the WH word and the gap where it's understood, and maybe it looks something like this. Okay, trying to build this. So, okay, we're going to build it from what kind of building blocks? Well, blocks can be really, really small, so that many of them make up a WH dependency. And it may be slower to put together many small blocks because there are many of them, but maybe these blocks get reused a lot, right? They get reused in like a lot of different dependencies, and so that makes them faster to access in the first place. Now, the other extreme is maybe blocks are really, really big, in fact, so big that only one makes up a WH dependency. Now, in this case, of course, it may be faster to quote-unquote put together one big block. You're not putting together anything. You're just done, one and done, right? But maybe it's slower to access that block if the block is used rarely. Basically, if you have, in some sense, one per WH dependency, maybe it's not so easy to grab them because you don't grab them that often, right? So you have these balances of things that make it fast and things that make it slow. And so the idea is that the most efficient option is probably a balance of bigger and smaller blocks that collectively are faster to access and put together. So, here's just one example, but pick your building blocks. Find the building blocks that make it faster on average to build whatever WH dependencies you encounter. So how can children find the best balance? This is a great question. In this case, one way is to use Bayesian inference to search through the hypothesis space of all possible building blocks and find an efficient set for children's input. Now, there's just to kind of quell any worries you might have about how plausible is this Bayesian inference thing. Turns out there's a considerable body of evidence suggesting that young children are capable of Bayesian inference or approximating this mental computation as best as they can and doing it pretty well. And human cognition in general there seems to be a variety of evidence that human minds can do something that looks like Bayesian inference. So our modeled learners here, using this learning theory, are going to be using Bayesian inference to try to find the best building blocks. So that's, again, what our modeled child is going to be doing. So we'll see if this modeled child can learn the target knowledge that real children seem to learn.